Hello. Hello. So I'm going to give you a lightning talk on a very PROGCRYPTO aligned topic, which is work by me and colleagues Dimitri, Jean-Fei, and Mary. And it's very PROGCRYPTO aligned because it is it includes recursive snarks and also the Ethereum consensus layer. So I'm going to start by introducing how the consensus layer of Ethereum works. Then I'm going to present a problem that we have right now, and then I'm going to walk or more like run over a few possible solutions using recursive snarks. Right, so let's get started. So proof of stake and consensus, proof of stake consensus is essentially like a voting protocol. Like validators vote on what the next block should be. So Alice is like, I want the next block to be that. And people vote. And in the end, because we have validators, the winning block is basically the winner of the election. So here we're going to deal with election protocols in this talk. And in these elections, we use digital signatures to vote on things. So people vote, and they sign the block that they believe in. So Ethereum currently has about 800,000 validators. So this is like a big number of validators. And this means that digital signatures on their own is not sufficient. We need to boost them. So we use a scheme called BLS signatures, which is a signature scheme that has aggregation. Aggregation means that if you have two signatures that sign the same message, you basically put them into one signature. You aggregate them into one signature, and then this signature can be verified in place of two. And this is very nice because, when you have 800,000 validators, you don't want all the signatures to be flying around. You want to aggregate them and to minimize verification cost and bandwidth. So on the consensus layer, what we have is we have voting rounds where people send signatures, they get aggregated by an aggregator, and the aggregator spits out an aggregated signature, but they also they also need to show people who voted. So they need to be able to show people that Alice, Bob voted, but Charlie didn't vote. And Ethereum does this using bit fields. We use bit fields basically to say we use one index per validator, and if it's 1, they voted. If it's 0, they didn't vote. And when we're dealing with this amount of validators, these bit fields get quite big, and 1 million bits starts adding up to the size, and validators are already bandwidth constrained. So these bit fields, they might seem innocent, but they are actually the whole topic of this talk. Right, so how the consensus actually works is because bandwidth is hard and voting is hard. Basically, not everyone votes at once, and instead we just chunk up the validators. We have 1 million validators, we chunk them up into chunks, and then these chunks vote one by one. So 10,000 validators vote in one time, then the other 10,000, then the other 10,000. How they do it, it's not so important for this talk, but the fact that we chunk them is important. Right. So there is another thing called single slot finality, which is basically the consensus researchers' dream. It basically, consensus people, they're if you have a town with 1 million people and you want to throw an election, you don't want to do an election every day, a mini election every day to do an election. You want to do a big election one day and get done with it. Because if you do a mini election every day, you don't know what happens between the days. It gets much more complicated. So sort of the question becomes, and the question that us as cryptographers are trying to solve is like, how can these 1 million people vote in one go? And like, it's not even 1 million people. Like, in the future, maybe like in a year or two, there will be many more than 1 million people. And because the validator set keeps on increasing. So, you know, in a year it will be 2 million, and who knows where that's going. So building primitives for aggregation systems is extremely important for the Ethereum consensus right now. And we're not going to go too deep into how these systems work, because this talk is very, very small. But like, I'm going to give you a straw man approach of how aggregation could work in such a system. So we're going to be working with like a system where in the beginning of the protocol, on the top level, people send signatures, they vote with signatures, and then people take the signatures, they aggregate them, they send them forward, the next person takes the aggregates, they aggregate them, they push them forward, the next text, like this sort of chaotic gossip-based protocol. Let's use this for the rest of the presentation, because while we don't use this right now, it has certain benefits, and it also serves as a good test bed to demonstrate the problem. So in this protocol, we start with signatures, but then as the protocol goes on, we deal with aggregates, and as the protocol goes on, the aggregates get bigger and bigger and bigger. And now if we focus like on the bottom left part of this, like this guy on the bottom, they're basically, you know, somewhere in the middle of the protocol, and they just got 2 aggregates, and they need to aggregate it. You know, like aggregating the signatures is easy. Like you just add them up. BLS is good at that. But the bit fields because it's not something that the BLS scheme is supposed to do. BLS is just a signature scheme. It's not supposed to do consensus. It is much more tricky, because like you have these two bit fields. You see that the bit fields have like the first index is active on both bit fields. So like, what do? Do you just add them up, but then you get 1 + 1, 2, and it's no longer a bit field, and it's bigger, heavier. To send this thing on the network, it gets bigger and bigger, and then maybe it goes to 3, to 4. So because validators are like resource constrained, this is not what we want to do. We don't want to just add them up. Another approach is to just take the union. You know, like if you have 1 in one bit field, just put 1 in the final bit field. But that also doesn't work in our case, because the BLS verifier would not verify. Like, the BLS verifier actually needs to know if it's a 1 or a 2 here. And this sort of problem with the bit field, we call it the bit field merge problem, and it's what our work focuses on. And for this reason, we basically start by introducing a formal scheme, sort of like an API, for how a signature merge scheme should work. Basically, a scheme that is able to take signatures and bit fields, merge them as we want them to be merged, and produce bit fields as output. You can see these weird things I put on the slide, the PROGCRYPTO things, because now we're starting to go from like sort of like traditional cryptography, where we just design like a simple signature scheme, to something a bit more like twisted. Like we start adding bit fields, we start adding more like semantics. So, and in our post, because we have written a post about this, we introduce this scheme, and then we propose 3 different instantiations using recursive snarks. And the idea is that basically, you know, let's just forget about BLS entirely. We don't need BLS anymore. If we have fast enough recursive snarks, we can just do the aggregation with the snarks. And to go even more PROGCRYPTO vibes, like we're going to use recursive snarks plus like proof-carrying data, which is a paradigm which basically tells you like that the data of your system travels along with proofs that testify to their correctness. And in our scheme, what correctness means is essentially that, if at some point in your protocol you see a bit field and it has a 1 somewhere, this means that someone has voted that message, that someone has voted that message, and it should only have 1 if and only if we have seen a signature from that person. And this sort of like property, this sort of property, because we use proofs in a recursive manner, it inductively follows to the beginning. And so we are basically trying to design a proof-carrying data system using recursive snarks that allows us to, take proofs of correctness, produce proof of correctness, and pass them forward. Right. And in our post, we have 3 different approaches that go from the simplest but heaviest to the lightest but more complicated. And I'm not going to go too deep into this. I will have the URL for the post in the end. But the first approach is just like a full recursion. Like you just build a circuit that verifies proofs, and it spits out proofs and bit fields, and it sort of recursively works together in a way that allows proof-carrying data, but it's very expensive. Like the verifier box inside the big box is a very big box, basically. It is, I'm lying about how small it looks there. It's actually like verifying proofs inside proofs is very expensive. So what we do is then we look at the next evolution of this concept, which is a paper called Halo by Zcash, which is effectively, instead of fully verifying the proof inside the snark, it just partially verifies it and accumulates what you haven't verified yet forward. So this allows the prover to be much slimmer because you don't do the full verification. You just do a bit of verification, and then you accumulate forward, and every recursive step you accumulate, and at the end of all the steps, you just need to do one big verification. And this is slimmer and a bit more complicated than before, but the trade-offs seem like worth it for us. And if we want to go one step forward to make it even slimmer, we would need to go into folding schemes, which is like this new paradigm from the last 3 years where you don't even actually deal with proofs themselves. You just deal with instances of the relation, and you fold those together, and you accumulate those. So it's even slimmer because you never go into the proof system. You never have to, at each recursion step, you don't need to like invoke the proof verifier. You don't need to do any of that. So this is like the simplest, the slimmest thing, the fastest for the prover, but folding is not created right now with the proof-carrying data in mind. Like, if you try to adapt this paper, the Nova paper, for proof-carrying data, it's actually quite hard to do. And like, things don't work out. Like, you need to change the relation. You need to figure out how the lookups are going to work. You need to deal with, if you have a big witness, you pay in communication cost. If you have a big instance, you pay in computation cost. Like, it feels like a very nice tool that hasn't been ironed out perfectly. And in our post, we throw out a few open research questions. So I think as I'm closing, like, first of all, you can see the URL of our post on the bottom, some bottom direction anyway, that you can look into. And in that post, we throw out a few open research questions on how we can do PCD with recursive snarks for the consensus layer and issues we have encountered while doing so. So yeah, I think this is the rough summary, and if you want to learn more, just read our post.